So climate modeling is a broad term describing the interaction between the atmosphere, ocean, land surface, ice caps, and solar installation on the Earth. So when we have a climate model, we basically have a model of the Earth. And then we can investigate how the climate has evolved in the past, and we might see how it evolves in the future as well. For example, sea level rise and global warming. Since climate models include many processes, we need large computing resources. And in fact, all the largest supercomputers in the world are all designed for climate modeling. The model we use is called the CSM, or the Community Earth System model. It's a coupled model that combines all the dynamics of the climate system. The CSM requires substantial amount of resources. For example, a low resolution run takes around a day to simulate 30 years. CSM is used for climate research at universities around the world, and it is one of the main climate models used for the international IPCC reports. At the Niels Bohr Institute at the University of Copenhagen, we mainly use CSM for research of past climate and for better understanding of the dynamics of the ocean. My own research is on the impact of so-called near-inertial waves in the Arctic and how they might affect the mixing of the upper layers of the ocean. One of the deficiencies of climate models is that they underestimate the rapid sea ice loss in the Arctic. This means that in the Arctic, the sea ice is melting much faster than is predicted by the models. The near-inertial waves might be able to explain part of this rapid sea ice loss. To improve near-inertial waves in CSM, we have increased the coupling between the ocean and the atmosphere from 24 hours to just 1 hour. This means that the wind stress, which is driving the near-inertial waves, is much better represented. And where the near-inertial waves previously was only half of the observed, they now correspond to the observed values.
SESAM is composed of many lines of code and incorporates 7 different geophysical components. It can be used to model thousands of years into the past and future. Our goals were to profile SESAM for performance bottlenecks and later port heavy computations to the GPU. The impact for simulations is clear. As a first step, we had to migrate SESAM to work on the local cluster at MBI. It was a fresh install and there were several issues with GNU compiler support, external libraries, and final integration with Slurm and MPI. To evaluate GPU integration, we had 2 tasks: profile real simulations and become familiar with the software architecture. We decided to go with architecture analysis as some of the simulation parameters were not available initially. SESAM is a fully coupled model, combining output from all of the 7 geophysics components. Being independent of each other, the coupler is used for synchronizing between components. The components are running in parallel and on each cluster node. There is no control over allocation of CPU core to component process through MPI or SESAM. The question is how to synchronize access to the GPU for multiple components. Components can get different amount of processors in a specific run, since some might be heavier to compute than others. All these topics were more advanced. We still need to integrate OpenCL with Fortran for the simplest task. Some research was spent over different methods to accomplish that. Finally, the ISO-C binding extension introduced by Fortran 2000 was found to solve bridging issues between C and Fortran. CL Fortran was started to port OpenCL interface to native Fortran with no C code involved. You can see in the example a Fortran call to an OpenCL function, similar to C and using the CL Fortran interface. Detailed profiling still has to be done, and it requires deep analysis of the code to employ GPUs efficiently. In addition, a method must be chosen for node-level synchronization to protect GPU access. And yes, GPUs are really a challenge and an opportunity, but we are one step forward to make it easier.